Hello everyone, and welcome to my presentation. Today I am very excited to show you my Pathfinding Visualizer. This is a fully interactive desktop application that I built entirely from scratch using Java Swing. The primary motivation behind this project was educational. In computer science, we spend a lot of time studying graph theory and search algorithms like breadth-first search or Dijkstra's. However, we usually only see the results as abstract text in a console window. I wanted to build a visual learning tool that bridges that gap, something that allows students to actively watch these algorithms, think, navigate, and process data structures in real time. Under the hood, the project is structured with clean software engineering principles in mind, separating the graphical user interface, the grid model, and the algorithms into their own dedicated Java packages. UI, interactions, and breadth-first search launch the application. As we open the application, you'll see the main interface, a clean 25 by 40 interactive grid. At the top, we have our control panel, where we can select our algorithm, adjust the animation speed, and manage playback. There is also a color-coded legend so the user always understands the state of the board. Let's set up our environment. By left-clicking, I place our starting point, the green node. A second click places our destination, the red node. From here, I can click and drag to dynamically draw walls, creating a custom maze. If I make a mistake, right-clicking and dragging acts as an eraser. Let's test our first algorithm, breadth-first search, or BFS. BFS utilizes a queue data structure. As you can see by the expanding blue cells, it explores the grid layer by layer, equally in all directions, almost like a ripple in a pond. Because it searches uniformly, it is mathematically guaranteed to find the absolute shortest path on an unweighted grid, which it then highlights in yellow. Depth-first search in Dijkstra's algorithm. Click Reset now. I'll keep the walls but clear the visited cells so we can contrast BFS with depth-first search, or DFS. Notice the immediate difference in behavior. DFS uses a stacked data structure. Instead of searching broadly, it aggressively plunges down a single path as far as it possibly can. When it hits a dead end or a wall, it backtracks just enough to find a new path and plunges again. While DFS is highly memory efficient, this visualizer perfectly demonstrates why it does not guarantee the shortest path. Next, we have Dijkstra's algorithm. While Dijkstra is famous for finding the shortest path on weighted graphs using a priority queue, in this unweighted grid, you'll notice its behavior looks quite similar to BFS, exhaustively searching all available avenues until the target is found. A search, edge cases, and future workstar. Finally, let's look at the most optimized pathfinder in this tool, a star search. A star is smart. It uses a priority queue combined with a Manhattan distance heuristic. Instead of searching blindly in every direction, it calculates the estimated distance to the target and actively prioritizes paths that move it closer to the red node. As you can see, it finds the target by exploring significantly fewer cells than the others. The application is also built to gracefully handle edge cases. For instance, if I completely box in the start node with walls and run a search demonstrate trapping the start node, the algorithm will explore the confined space, recognize that the target is unreachable, and cleanly halt the animation while presenting a no path found dialog to the user. Moving forward, I plan to expand this project by adding weighted terrain like swamps that cost more to move through, as well as automated maze generation algorithms. Thank you so much for your time.